So in the last lecture you have seen the introduction to heat exchangers. You have also seen several different types of heat exchangers. Now we must move on to the analysis of heat exchangers. So before we proceed, we must first understand what is overall heat transfer coefficient. Now, one thing which you have noticed, so we are on slide 28 right now, and this is section 2. So one thing which you have noticed in different types of heat exchangers which you have seen, the common thing which connects them is the broad configuration that there is a hot fluid, there is a cold fluid. These two are flowing inside ducts or chambers which are closed somehow. And then there is a wall, either a metallic wall or a solid wall or a ceramic wall or some type of a wall which separates the two fluids. So we don't want to mix them, so therefore they have to flow in a separate containers in ducts or tubes or shells or plates or passages, and the wall is there in between. So essentially the heat transfer takes place from the hot fluid to the cold fluid, passing through from the hot fluid, convectively getting transferred to the wall, then going through the wall, and then finally going to the cold fluid. So in this series or the path of heat transfer, what is the total resistance? What is the overall resistance is what we need to understand. So we are on slide number 28, moving to slide 29. So here you see a diagram of a simple tube-in-tube heat exchanger. Any other heat exchanger will have a similar configuration. The only thing is that this common feature of a hot fluid, a cold fluid separated by a wall will remain common to all types of heat exchangers. So as I was saying, the heat exchanger involves two flowing fluids separated by a solid wall. Now heat is transferred from the hot fluid to the wall by convection. So the first you have the high temperature Ti, which is the internal pipe with flowing where the hot fluid is flowing. So the heat, as I was saying, it will get convected to the inside of the wall, and this will require some delta T depending on what is the Reynolds number of the flow, what is the Prandtl number of the system, and things like that we have seen in the earlier lectures. Then the heat will pass through the wall. Again, here it will be pure diffusion. There is no convection, it's a solid wall. There will be a delta T again depending on the geometry of the wall and its thermal properties, that is K, rho and Cp. And then again you have the outside environment or the cold fluid inside the outside on the outside, wherein the convection will take place. So if you see the passage of heat transfer, you have three major resistances. Mind you, any radiation effects there may be radiation on the outside, for example. Also in inside also, these two are at different temperatures, so they will radiate with each other, but we will neglect them. In fact, neglect is not the correct word. We will include their effect in the heat transfer coefficients and adjust them accordingly so that the radiation is also taken into account. We will not invoke any radiation equations when we are analyzing the heat exchangers. So the primary resistances are three. The resistance inside, the convective resistance because of the inside flowing fluid, which is hot in this case. Then the diffusion resistance, and then finally the outside resistance. And they are connected in series because the heat has to go from high temperature to low temperature, and it has to pass through these three materials, a medium, to finally establish a steady state type of a temperature difference between the hot and the cold side. So moving on to the next slide, slide number 30, we now want to quantify these three resistances, and the outside and the inside convective resistances are easy to quantify. They are typically scaled by 1 upon HIAI, which is the internal resistance Ri, and the outside resistance is Ro, which is 1 upon HO into AO. As regards the conduction resistance, which is in the tube, inside tube having a diameter of DO outside diameter and DI inside diameter, you will recall from our conduction analysis in chapter 1 and 2, in fact, we tried to quantify this, and it comes out to be the resistance at the wall is ln do upon di divided by 2 pi k into L, where k is the thermal conductivity and doi and di are the respective diameters. So if you add the three resistances in totality, it comes out to be R is equal to R total, Ri plus R wall plus Ro, which is 1 upon HI plus ln d0 upon di divided by 2 pi kl, which is the diffusion resistance in the cylindrical coordinate system, which we have derived long back, and plus 1 upon HOAO. Naturally, the AI and AO are the respective heat transfer areas, which are pi into di into L for the inside portion of the pipe, and pi and A0 or AO will be equal to pi into DO into L, which is the outside of the pipe. You will recall the diagrams which I showed you. In many cases, we would like to, of course, reduce this thermal resistance. So one of the ways of reducing is, of course, to make this wall made up of copper, for example, or some good thermal conductive material, and as thin as possible, so that the pressure and the other mechanical loads which are coming, it is able to take it. So in many cases, the two heat transfer surface areas associated with the double pipe heat exchanger are in fact such that di and do are almost the same, and therefore the AI and AO are also identical, and therefore this resistance, this diffusion resistance, may be very small, almost negligible in many cases. So this drop of temperature within the pipe may be negligible, but may not be negligible also. So one has to see the real, the actual condition when you are doing analysis, and of course when you are doing synthesis, one has to see other issues also to take into account to get the thickness of this wall correct. So let's move on to slide number 31. Here the same view now is a much clearer way it is shown. So the total Q which goes out from the inside temperature, which is hot, to the outside temperature, which is the cold fluid, will be simple. You have all the three resistances in the denominator. You can see R1, R2, R3. The R2 is because of the wall. Here it is given in terms of radii, which is the same. In previous slide it was in terms of diameter. So essentially is the same thing. And this thickness can be almost zero or very small, and therefore this resistance may be negligible as compared to the other two, which are the convective resistances. You will also recall that the heat transfer coefficients of let's say liquids as compared to air is usually higher, or gases. So one of them may have a gas. So accordingly, one of these resistances can be very high. So let us move to slide number 32, wherein this is discussed. So first of all, if R wall is equal to 0, on the right hand side I am showing the figure, and AI and AO and are equal, and let us assume it to be equal to A surface, then essentially the diffusion resistance due to wall goes away, and you are only left with HI and HO. So how do we define the overall heat transfer coefficient? We can write something like that. So Q is equal to delta T upon R, which is like the classical statement, where R is the thermal resistance and delta T is the potential required to drive this Q dot, which must be equal to, in simple cases we write HA delta T, but in this case we will write UA delta T, wherein U will represent all the resistances which come in the process of heat transfer from the hot fluid to the cold fluid. And naturally this will be equal to either UI AI delta T or UO AO delta T, because Q is a constant, it is a steady state heat transfer. So what goes from inside must come outside. Outside, of course, the area is larger, but accordingly the UO will become smaller, and therefore you will see that this equality will also hold. So when you write or cast the equation in such a manner, U is the overall heat transfer coefficient. Mind you, it is exactly like H. However, H is H is only used when a single fluid transfer and a single wall we are dealing with. Here we have multiple, let's say, resistances, and each resistance is added up, and the combined resistance is written as uh, 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 let's say 1 upon U or 1 upon UA, if you see this equation. So therefore 1 upon UA is equal to 1 upon UIAI is equal to 1 upon UOAO, because AI and A0 can be same for a very thin wall. And therefore the R is equal to, if you write R, the R wall may be dropped, and you are left with 1 upon U is equal to 1 upon HI plus 1 upon HO. So now there are three resistances, one because of the convection, one at the inside, one because of the convection outside, and one the wall. Wall can be there or it may be neglected depending on the actual, let's say, magnitude of these three resistances. Now which one of them is dominant? So we can discuss this. The overall heat transfer coefficient is dominated by the smaller convection coefficient. So you can see here, let us say if you have air on the outside and a very fast flowing fluid or water, let us say inside, at a very high Reynolds number. So naturally this HI will be very high. So when HI is high as compared to HO, there may be an order of magnitude difference also. Then naturally 1 upon HI will be a very small quantity and 1 upon HO will be the larger quantity. Okay, because HO is the smaller of the two. And therefore when you add it up and reciprocate, that is 1 by U becomes U. At that time the dominant portion of this U will be because of the HO. So when one of the convection coefficient is much smaller than the other, that means HI, let us say for example HI is smaller. It can also be the reverse, HO can be smaller. We have 1 upon HI is far greater than 1 upon HO, and thus U minus U is equal to HI. That is, the situation arises frequently when one of the fluids is a gas and the other is a liquid. Therefore, you will always see that the fins are used on the gas side to enhance the product UA, and thus the heat transfer on that side. So the question is, where should we add the fins? Should we add the fins inside or should we add the fins outside the tube? So the answer is very simple. The answer is that wherever the heat transfer coefficient will be low, we would like to add fins on that side, so that the product, the thermal resistance 1 upon UA actually becomes lower. So moving on to slide number 33. Which actually lists down some of the common values, of this overall heat transfer coefficient, which can range from a very small value, with air with natural convection, for example, in those type of heat exchanger, air to air heat exchangers or gas to gas heat exchangers, and it can be of the order of 10 to the power 4 or 10 to the power 5. Depending on whether we are doing some phase change or evaporation or condenser, where the heat transfer coefficients are usually very, very high. So you see some of the representative values. Let's say water to water, it is of the order of, let's say, 850 to 1700. If you go down this thing for steam condenser, it can be from 1000 to 6000. These are typical values which you get in a new condenser. As the condenser becomes old, there will be some fouling on it. So we will talk about fouling in a later lecture, so that some more resistances will be added in the series, and this may come down from 6000 to 4500 or even lower. Then for example, you have steam to air in fin tubes. You can have very small 30 to 300, for example. Similarly, gas to gas or water to air, it can also be pretty low. So you should have a certain feeling of these values, because if your answer, for example, for a condenser, if your numerical answer comes out to be 15 or 20 or 30 watts per meter square Kelvin, then you should immediately realize that something is wrong, because a steam condenser will never have such low heat transfer coefficients in real time. So moving on to slide 34, here you see several examples. I have tried to put many figures so that you also come to know that usually the heat exchanger tubes, especially when you are using a gas or a air, they will always have some fins. Now the fins may also be sometimes inside, because you may have a refrigerant flowing and you may like some turbulence also, and some extra fins. You can see here that the fins are actually inside also as well as outside. So this decision has to be taken. It's a techno-economic decision. On one side you want to maximize the heat transfer coefficient, but on the other side you don't want to employ a tube which is very expensive to manufacture. So you have to do a trade-off. There are certain tubes which have only fins on outside and they are smooth from inside. There are also special structures like this which are created when you create an outside fin. There is already internal serrations which are created, excuse me, during the operation manufacturing place. So now whenever there is a fin, how do we account for the area? You have this area inside and area outside, which you have to calculate to get the heat transfer, overall heat transfer coefficient. So when the fin tube is finned on one side to enhance heat transfer, the total heat transfer surface area on the fin side will be A fin plus A unfinned. So for example, you see fin here, there is the fin area, the area of the fin, that is the enhanced area, and then there is some gap in between the two fins. So the cylinder is, there is no fin on that cylinder, which is the internal pipe. So this is the unfinned area. So for short fins of high thermal conductivity, we can use this total area in the convection. So whenever you calculate 1 upon HA, this H can be inside or outside. Wherever there are fins, you have to, so whenever you are using fins, so that appropriate area you have to calculate. So how do we calculate that area? The net area AS is the unfinned area, which is the bare area between the two fins of the cylinder or the pipe, and plus eta fin. You remember the efficiency of the fin which we have derived, because the entire area is not being used for heat transfer. In fact, if you remember, uh, it's a combination of sine hyperbolic and cosine hyperbolic functions. So as the length of the fin becomes larger and larger, the advantage is not that high. So you have the eta fin, if you remember, the efficiency of the fin which we had defined, so into the area. So whenever I give you a problem wherein you have a finned surface, then please use this area either outside or inside, depending on where the fin is located. Moving on to number 35, which is the last slide now. So we have defined in this lecture the overall heat transfer coefficient. We have also seen how the overall heat transfer coefficient can be calculated. And whenever there is a finned surface, you have to be extra careful about considering the area of the fin and the fin efficiency. Here I end this lecture. I leave you with two pictures wherein you can see very large heat exchangers for chemical process industry, which are being transported from one location to the other for erection, like a shell and tube heat exchanger, for example. And you also see on the right a plate fin heat exchanger, which is also fairly large for a heavy duty operation. And you can see the serrated fins. You can see the inlet outlet ports also. Alternate let's say the gap between alternate tubes is filled with hot and cold fluid. So they are stacked together. And we would like to know the overall heat transfer coefficient under such conditions. So with this, I close my lecture number 2 at slide number 35. So in the last lecture, we have seen the three primary resistances which come in a heat exchanger. That is the convective resistance and the conductive resistance in the wall, which separates the two hot and cold fluids. Now that was an ideal heat exchanger. In a real heat exchanger, there are some additional issues which come, and we must see them and appreciate them and try to include that in the analysis also. So in this lecture, which is we are on slide number 36, we will see what is called as fouling. What do you mean by fouling, and how do you incorporate that in the analysis of the heat exchanger? So moving on to slide number 37, here is a figure in which we see the ideal heat exchanger, in which a cold fluid has two walls on the both sides, and then across the walls there are hot fluids flowing. And in a new heat exchanger, naturally the surfaces are clean. Now the performance of such heat exchangers deteriorates with time as a result of accumulation of deposits, which you can see on the figure on the right hand side. So you can see the deposits on the wall over a period of time because of several reasons which we will discuss. So these the layer of deposits represents additional resistance. So imagine heat flowing from the hot fluid to the cold fluid. So we have the convective resistance at the hot side, then the conductive resistance in the tube, followed by the convective resistance in the cold side. Now, if there are deposits which are adding on to the wall because of several reasons, then as the heat flows, it will encounter this additional material which has come. And this is what is fouling. This is the additional resistance which come. So this resistance is usually represented by a term called fouling factor. And as we have seen in the last lecture, upon 1 upon UA, which is U is the overall heat transfer coefficient, is equal to 1 upon UIAI is equal to 1 upon UOAO, because in steady state, the Q which gets transferred in the outside is the same as what Q is transferred to the inside, which is equal to R. So we can write this R. We have seen the three terms, the 1 upon HIAI, then your the ln do upon di. This is the conductive resistance of the cylinder or cylindrical pipe, which comes in between, and then the outside. Now what we are introducing here are another two additional resistances, that is RFI, which is the resistance because of this fouling which has occurred on the inside, and RFO, which is on the outside. So these two are the additional resistances which have to be added up, and sometimes, as you will see in this lecture, sometimes these resistances can be pretty high as compared to the other resistances also. And so over a period of time, the heat exchanger, whatever design you had done or design calculations you had done, may not remain applicable unless you have actually taken this fouling into account over the life cycle of the heat exchanger. So let us move on to slide number 38 and see how do we quantify it and what are the implications of this fouling on the overall performance. Now, before we go, let us see what are the reasons of these fouling, what are the different types. So the most common type of fouling is the precipitation of solid deposits in a fluid on the heat transfer surfaces, which is also called as scaling. You must have seen in your home also that the old stainless steel utensils, when you buy from the market, they are pretty clean and they are shining. But if you continuously use a particular stainless steel or iron vessel, or even an aluminum vessel for boiling water, then you will see that after a while there are scales which get deposited, whitish material, which is calcium, typically scales of calcium or magnesium salts on the utensils, which gets deposited. And then such deposits come off by scratching. Sometimes they are very difficult also. Sometimes some acid treatment, you must have seen your mother cleaning it by a lemon juice, or some mild acid treatment can be done. That is the chemical treatment part of it. So similar things, now you can imagine large heat exchangers which have kilowatts or megawatt of capacity and used for power plants, for example. Almost 30% of the power plant capacity or the electrical power gets actually dumped in the river through a condenser. Then the rate of such deposits is rather high in real-time heat exchangers, and therefore you have to account for it, you have to understand it. And if you are maintaining a heat exchanger, then you must also do cleaning and periodic maintenance, so that this thermal resistance get periodically removed, or the resistance is treated, so that the overall resistance is manageable and it comes down back to the original design calculation for which the heat exchanger duty was designed. To avoid scaling, therefore, many times you have to do fluid treatment also. For example, water needs to be removed of the salt, so water has to be softened. So when we use for boiler water, for example, we use softened water. So there are water treatment plants which will do this to extend the life of the boiler, to also extend the life of the maintenance cycle, and to continuously make sure that the thermal resistance does not go beyond a particular level. Otherwise, the heat transfer will be reduced and our heat exchanger performance will be jeopardized, or it will go down. Also, severe scaling may also lead to damage of the tube itself, and then this will lead to leakages which may occur in boiler tubes. Scaling can also occur by gas flows. So you don't think only that liquid only will lead to fouling or these additional resistances, but even gases can do that, because the fuel gas, for example, may have some sulfur, and you may find that the sulfur dioxides are formed. Eventually they will react with the steam. H2O is also a combustion product. You may have sulfuric acid which can form, and it can lead to corrosion type. So that is the another type of fouling, which is corrosion or chemical reaction driven fouling. You can also have local electrochemical flows which can occur because of the presence of, let's say, salt water in a brass heat exchanger or a copper heat exchanger, for example. These salts may also lead to electrolytic flows, local eddy currents, and electrochemical deposition or electrochemical wearing or pitting or corrosion can also occur in heat exchangers. Another very important type of fouling is because of biological growth or algae. Also in marine heat exchangers, you may have marine animals which can form calcium shells or barnacles inside the heat exchanger, which is very hard. They are like the ceramic materials which gets deposited, coral or shells type of material, which these insects would like to make in the warm water, which gets stagnant inside a heat exchanger. For example, if you don't operate it for a very long time, then algae and biological fouling can also happen. Vegetative growth can also take place inside heat exchangers. So these are like real time important issues which we must take into account. So moving on to slide number 39, how do you quantify it? So usually experiments have been done. We also analyze this material for its thermal conductivity. You can see here a pipe with severely fouled. You can see the original thickness of the wall and now the thickness of the fouling which has occurred, the deposits which have occurred over a period of time. Now another important problem is that you can see here the diameter of the pipe gets reduced considerably because of this fouling. And if you want to maintain the same mass flow rate, now you need a larger pressure drop. So the pumping requirement goes up. So, and if the pump is not capable, then the mass flow rate gets reduced. And if the mass flow rate gets reduced, the Reynolds number gets reduced. The Reynolds number may change if the pumping power is not increased, and therefore the heat transfer again gets dropped. So you have not only the HO gets affected, there is an additional resistance because of conductive resistance also because of this fouling. Then this algae growth or corrosion or scaling is also a very strong function of the operating temperature of the heat pipe, of the heat exchanger. Also the length of the service, and it decreases with velocity of the fluid. So the fluid velocity, the Reynolds number, also affects the rate of growth of this particular fouling. So here you can see some representative figures, the representative fouling factors, which is the thermal resistance due to fouling for a unit surface area. So you can see it is your heat transfer coefficient is 1 upon h. The heat transfer coefficient is h. So 1 upon h is the resistance into meter square, and therefore 1 upon Ha is thermal resistance. So this fouling factor is watt per meter square Kelvin. So it is reverse of your heat transfer coefficient. So larger heat transfer coefficient means a smaller resistance, and therefore this RF in a way is a reciprocal of one of H. So 1 upon H has the same units as RF. So you can see here distilled water or sea water or river water, boiler feed water below 50 degrees, it is 0.0001, but as soon as the temperature becomes higher, the fouling factor becomes large, and you can see a very strong let's say function of temperature here. Similarly, fuel oil will also get, maybe some waxy deposits will come in the heavy oil or diesel oil mixture. They may also be a little acidic, which can react with this material. For example, then there are additives which may come out because of if water gets mixed with fuel, then coagulation also takes place. Some gummy materials may come and get deposited in fuel lines of heavy oil and diesel especially. Then you have steam flowing also will lead to fouling. Then refrigerants, the liquid side and the vapor side, you can see in fact the vapor side fouling is higher than the liquid side fouling in this case. And then alcohol and air also will have humidity and things like that. There will be particulate matter, aerosols, which will also get deposited on inside of the tubes over a period of time. There are also fibrous materials which are picked up in the air. If you don't filter them properly, then we will see some photographs in the next slide. So let us see, go to slide number 40. Here you see some examples. You can see fouling, severe fouling in fact, which can be corrosion, it is deposition, pitting, it can also be by chemical action. So you can see here the shell side, the shell side of the heat exchanger. Sometimes also when you are using river water and if you do not flood it properly, then the mud or from the floating river, the mud which is floating in the river water can also come if the filtration is not proper, and very fine deposits, muddy deposits can happen inside the heat exchanger, and you can see here some of these examples. In slide number 41, you see on the left, you have the air-cooled heat exchanger or compact heat exchangers, which have fins. And this is a very common example where you must have seen in your home also, that periodically, you see these such type of deposits which occur if the filtering is not correct. And there is a lot of humidity in the air. So you will see such type of deposits which take place. They can completely choke the air side. And some fungus can also grow here, which can be detrimental to your health if such a heat exchanger is giving cold air to your room. So this, you need to be careful. The delta P increases, the mass flow rate goes down, and the efficiency of the heat exchanger gets severely hampered because of such type of deposits. Now the cleaning, as I have seen, see here you can see the shell side choked, on slide 41. You can see complete choking also because of seawater biofouling. So you can see a lot of animals, these crustaceans, trying to make their colony here inside the heat exchanger. And this can be very, very difficult and detrimental to the health of the whole plant. A power plant which is using marine water for cooling of the heat exchangers or cooling of the engines, for example, or turbines. The cleaning is usually quite an arduous task. You need high pressure water jets, high pressure pumps, and a very strong directed flow, which can actually remove this type of material which is sticking to the metal. You may also need to circulate some acid, or some chemical treatment has to be done. Sometimes you also put some zinc or electrolytic material which gets eroded, and to protect such heat exchangers we may put some zinc which by electrochemical action will get easily reacted, and it will prevent the heat exchanger to react further. So many things have to be done. We will not go into further details, but as far as thermal analysis is concerned, it's an additional resistance. And as you can note from these figures, on slide 42 also, some plate heat exchangers, the fouling has been done. Here the tubes, the entry to the tubes has barnacles or marine deposits. So as you can see that the resistance values which you have chosen for the virgin design may be completely out of sync with the reality over a period of time. And sometimes these deposits can be very fast. In fact, they can just happen over a very quick period of time. So please remember, the fouling factors which are usually tabulated have to be accounted for. You should also remember the order of magnitude of these fouling factors. If you have not taken it, it is better to include them to a certain extent, because then the design will be conservative. Otherwise, you may see that whatever calculations you have done for the new heat exchanger will collapse very quickly after a period of 2-3 months only, when such a scaling will occur. So it is always better, it is always advisable to see what type of scalings are possible, and then historical data has to be seen, and these fouling factors have to be included in the chain series reactions which is happening inside the heat exchanger. So with this, I close this lecture. This is lecture number 2A. Slide number 43, by finally stating again that fouling is a real problem. This should always be considered at the design stage. And also, of course, considerable uncertainty exists in the values of the fouling factors. They should be used only as a guide in the selection and the evaluation of the heat exchangers to account for effects of anticipated fouling on heat transfer. So please remember that these values are only indicative, and you need to be a little bit more careful in choosing these values for real-time design. So with this, I close the lecture at slide number 43, lecture 2A. So we will continue our discussion moving on to section 3 now, which is the analysis of heat exchangers. We are on slide number 44. So now, whenever we talk about heat exchangers, there are essentially two types or two classes of two major classes of problems in heat exchanger design and analysis. As an engineer, you often find yourself in a position where you need to either select a heat exchanger that will achieve a specified temperature change in a fluid stream of known mass flow rate. That means the fluid streams, the fluids are known, what type of, suppose for example, you may have some, let's say, industrial hot water is available, and let us say some stream of water in a river or a pond is available. Air in the atmospheric, this thing is available, and you need to cool down a certain hot water which is coming from some plant. So this is where you will do the sizing problem. So such type of problems are called as sizing problems, wherein you select a heat exchanger that will achieve a specified temperature change. That means the delta T of the hot fluid or the cold fluid, whatever is the objective function, is specified to you. The client wants a particular delta T. He knows at what temperature the thing comes out of a system, and he wants it to cool down, or he or she wants it to cool down to a certain temperature range, and that is specified, and therefore you have to do a sizing problem. Now such type of sizing problems are dealt with by the method of log mean temperature difference or logarithmic mean temperature difference, or the LMTD. So we will of course spend a considerable amount of time on understanding this LMTD method. You already know the definition of LMTD. We will again go through it quickly in the next lecture, and then apply this method to find out how we can do the sizing of a heat exchanger. Now the other problem which can occur is that if you have a specified heat exchanger, that means the heat exchanger is available to you, You are supposed to predict the outlet temperature of the hot and the cold fluid stream in a given heat exchanger. So these type of problems are called as rating problems. So you have to rate the heat exchanger, which means that you have to predict the outlet temperatures, that what will be the temperatures if these two fluids pass through it in a certain mass flow rate. So such type of problems can be solved by another, let's say, elegant method, which is called as the NTU effectiveness method. So after we study the LMTD method, we will also study the NTU effectiveness method. So NTU means number of transfer units, and we will of course spend a considerable amount of time after these lectures to understand this effectiveness of a heat exchanger and NTU. What is NTU? The non-dimensional quantity. And we will see how we can use it to analyze the heat exchangers. So moving on to slide number 46. So we will be essentially doing these two types of problems in the next couple of lectures. So what do you mean by design or analysis of a heat exchanger? So to design or to predict the performance of a heat exchanger, it is essential to relate the total heat transfer rate to quantities of interest such as inlet and outlet fluid temperatures, overall heat transfer coefficient, and the total surface area of the heat exchanger. So when you do the sizing problem, you are actually predicting the surface area, what will be the total area required, or what will be the length of the tube required to attain a certain heat transfer. Since the mass flow rates are known, you can get the Reynolds number of the flow, because the geometry you are choosing the type of heat exchanger which you would like for a particular duty. So it's an iterative process, of course, but nevertheless, you want to sort of relate the heat transfer coefficient, the mass flow rates, the geometry of the system, the configuration of the device to what is the performance at the end, how much heat you are able to achieve in a given under the given boundary conditions. So for such type of problems, as we said, the LMTD method is a simple approach when the fluid inlet temperatures are known and the outlet temperatures are either specified by the client or readily determined from energy balance expressions. So when these temperatures are known, the inlet temperatures and the outlet temperatures, or what is the expected outlet temperature, if this is specified, then we will use, as I said, the LMTD method or the logarithmic mean temperature difference method for this class of problems, the sizing problem. Then it is also used for determining the size of the heat exchanger. That is what I am saying, sizing, to realize the prescribed outlet temperature. So for example, if you know the inlet temperatures and for a given size of heat exchanger, the outlet can be predicted. But then if that doesn't satisfy the client, then you need to increase the area so that there is more residence time inside the heat exchanger, and so you will get the desired outlet of either the hot fluid becoming colder or the cold fluid becoming hotter, whatever is the main objective function. You achieve that by the sizing problem. So this is how you will proceed. So let us try to understand it more, let's say, clearly in the next slide, which is slide number 47. Also, you must remember that, let us see under what assumptions we will do this analysis. So there are some major assumptions. The first one, of course, is to note that the heat exchangers usually operate for long periods of time with no change in their operating conditions. So more or less, once they are designed, they will continue to operate. Of course, as we have studied in the last lecture, the fouling may take place over a period of time and the performance may decrease a bit. But then routine maintenance is done to clean the heat exchanger also. So almost all heat exchangers are modeled as steady flow devices. So we are usually not bothered about the transient of the heat exchanger because it is small as compared to the total time in which the steady state operation is desired. In fact, it is minuscule, the transient. Then the mass flow rate of each fluid remains constant. Typically, pumps are used to supply the liquid unless there is a change in, let us say, the mass flow rates are not, let's say, moderated very frequently. But sometimes there is a change in the river water temperature, for example, and then the mass flow rate may have to be changed. But for most practical purposes, for hours together, the inlet velocity or the mass flow rate of the cold and the hot fluid will remain identical for continued period of time. Then the fluid streams experience little or no change in their velocities and elevations, and thus the kinetic energy and potential energy changes are also negligible. So this is also a common assumption under which we will do the following analysis. Then the thermophysical properties like specific heat of the fluid in general changes with temperature. We all know that. However, sometimes the temperature change may also be large, but for a given range, it can be treated as constant at some average value with little loss of accuracy. So for most analysis, we will assume that the thermophysical properties are constant. So some more assumptions are given in the slide number 48. That means one of them is that the axial heat conduction along the tube is usually insignificant. We will neglect it. And the outer surface of the heat exchanger is usually assumed to be perfectly insulated, so no heat loss. So essentially what is happening is the hot fluid loses its heat to the cold fluid, and whatever energy exchange takes place, it takes place only between these two flowing fluids and not with any other third party or third environment. So it is only the mutual. So what is lost by the hot water is supposed, or hot liquid is supposed, or hot fluid is supposed to be taken by the cold fluid. So these idealizations which are stated above are closely approximated in practice and hence are commonly employed. So most of the assumptions which we have seen are quite true, and under these assumptions our analysis will be based and we will get reasonable answers with such type of assumptions. The assumptions also make the analysis simpler yet meaningful. So we don't have to complicate it unnecessarily, and we need meaningful, let's say, performance parameters or sizing of the heat exchanger. And then of course at the end one can always do some factor of safety for taking into account some transients or some variations which might take place, and try to design a conservative estimate which is also economical, reasonably economical in nature. So under these assumptions, let us apply the first law of thermodynamics. So essentially what it requires is that the heat transfer from the hot fluid is equal to the rate of heat transfer to the cold one, because these are the only two elements which are exchanging heat with each other. So this is done in slide number 49. So here you see the rate of heat transfer in the heat exchanger when the heat exchanger is insulated, as we have just assumed, is Q dot is equal to U, which is the overall heat transfer coefficient, which takes into account the convection, all the three resistances, or even 5 resistances depending on whether fouling is also taken into account or not. So all the possible resistances which are coming in the direction of this, in the path of this Q dot, are taken into account in this U, into the area which is the appropriate area of heat exchange, and then delta Tm. So delta Tm is the appropriate temperature or mean temperature which is applicable throughout the heat exchanger. And we have seen earlier that it is the logarithmic mean temperature which is the true, let us say, indicator of the mean temperature, because as you are aware, the mean temperature actually changes in a typical heat exchanger as it flows. Now under certain circumstances, the mean temperature may not change also, which we will see soon. So in general, this U, which is the heat transfer coefficient, and delta Tm change along the heat exchanger in general. Of course, the area of the heat exchange AS remains constant once the heat exchanger is defined or designed or it is chosen. So now let us quantify further what happens to the individually to the two fluids which are flowing. So you can write Q dot is equal to m dot C. So the C, let's say, the subscript C corresponds to the cold fluid. So Q dot is equal to m dot C. This is the mass flow rate of the cold fluid into CPC, which is the specific heat of the cold fluid, into TC out minus TC in. So that is the cold fluid will become hot, and therefore TC out will be hotter or larger than its value will be larger than TC in, because the cold temperature will cool down, will become hotter as it passes through the heat exchanger. So this is the heat which is absorbed or taken by the cold fluid. Now this must be equal to what is lost by the hot fluid, and naturally the delta T here will be TH in minus TH out, because the inlet temperature of the hot water or the hot fluid is higher than its outlet temperature as it passes through the heat exchange. So this much amount of heat, which is exactly equal to the what is gained by the cold fluid. So these two equations must be identical. And in the heat exchanger analysis, it is usually very, let's say, convenient to sort of club the m dot C, which is the thermal mass. So m dot is the mass flow rate and Cp is the specific heat. So mass into specific heat is the thermal inertia, indicator of the thermal inertia or the thermal mass of the system. And we usually club them and call this and term it as capital C. So this small c is the specific heat at constant pressure of the liquid or the fluid, and this Ch is the thermal inertia, which is so m dot h into Cph, and similarly capital Cc will be equal to m dot c and Cpc. So you can write this equation as Q dot is equal to Cc into delta T cold, and that is also equal to Ch into delta Th. So moving on to slide number 49. Now, so as we have seen, it is convenient to combine the product of the mass flow rate and the specific heat into a single quantity, which is called as the heat capacity rate. Now the heat capacity rate of a fluid stream represents the rate of heat transfer needed to change the temperature of the fluid stream by 1 degree as it flows through the heat exchanger. So this is the mass flow rate multiplied by the specific heat, and therefore it is, in other words, it is the amount of heat which is required so that the temperature changes by 1 degree centigrade. So what will happen now? Suppose we are comparing the heat capacities of the hot fluid and the cold fluid. So naturally, for a heat exchanger, the fluid with a large heat capacity rate will experience a small temperature change because its thermal inertia is very high. The m dot is high, the Cp is high, or the multiplication of the two, which is the heat capacity rate, is actually high, and therefore it experiences a smaller delta T. So please note that as soon as you have a higher thermal mass, then it is natural to say that this particular fluid out of the two, out of the hot and the cold fluid, the one which has a higher heat capacity rate will have a smaller temperature change, and vice versa. So now what happens if Cc is equal to Ch? So just to look at this diagram here, it's a counterflow heat exchanger, and you can see that the delta T1 and delta T2 are actually identical. Why does it happen? Because Ch and Cc are the same. So if Ch and Cc, the capital Cc and capital Ch are the same, or they are identical, then what will happen is that the delta T's will also be identical, and it will be a constant temperature change between the fluid. That means as you pass through the heat exchanger, the delta T remains identical. So whatever is the inlet delta T remains throughout in a countercurrent heat exchanger, for example. So delta T is equal to delta T1 is equal to delta T2, which is equal to constant. So the only time the temperature rise of a cold fluid is equal to the temperature drop of the hot fluid is when the heat capacity rates of the two fluids are equal to each other. Otherwise, in all other, and this is true for any type of heat exchanger for that matter, and for all other conditions, and then mind you, the capital Cc can become equal to capital Ch by the combination of mass flow rate and specific heat. So in certain cases mass flow rate can be low, but the specific heat actually is high, and therefore the multiplication comes to a value which can be made equal to the hot fluid value, and vice versa. So keep this in mind that the only time this can happen is when the capacities rates are similar or identical. Now, as you will recall, we have discussed so far only those heat exchangers where sensible heat transfer takes place in both the fluids. But as we have also noted in the earlier lectures, some of the heat exchangers can have boiling and condensation also, and the heat capacity rate of a fluid during a phase change process must approach infinity since the temperature change is practically zero. So you can see here a condensing fluid, there is the delta T is practically zero, and therefore the heat capacity rate is approaches infinity theoretically. And similarly in a boiling liquid also, the fluid is boiling, the hot fluid is undergoing a sensible heat transfer. It can be air, for example, and water can boil because hot air is passing over it, and water will start boiling at a constant temperature, and therefore the heat capacity rate of the boiling water here will tend to be let's say theoretically as infinity, because the delta T is actually zero, and whatever heat you supply from the hot fluid to the boiling fluid, it will directly lead to a phase change process, and therefore Q dot is equal to m dot HFG will be the guiding equation as far as those heat exchangers where phase change is happening. So with this background, we will now start the LMTD and the NTU effectiveness method, understanding them. What we have understood in this lecture is that sizing and rating are two important problems in heat exchanger design. The heat capacity ratio is also a very critical and important parameter for analysis, and we will continue to use it in both the methods. And the appropriate form of mean temperature difference between the two fluids exchanging heat with each other in a heat exchanger is logarithmic in nature. We have also specifically proven this when we were doing internal flows, chapter 8. And we will again do it once again for your clarity in the next lecture. So with this we close micro lecture 3 at slide number 53.